In this video, which is structure 1.1.3, we're going to look at two temperature scales, which are the Celsius scale and the Kelvin scale, and then we'll look at observable changes in physical properties and temperature during changes of state. So we'll start by looking at the two temperature scales. So on the left in this diagram we have the Kelvin scale, and on the right we have the Celsius scale. The Kelvin scale is an absolute temperature scale, which means it has the lowest value of 0 Kelvin. Ice melts at 273.15 Kelvin and water boils at 373.15 Kelvin. If we compare this to the Celsius scale, we can see that absolute zero on the Celsius scale is minus 273.15 degrees C, and water freezes at 0 degrees C, and then water boils at 100 degrees C. So next we look at how to convert from degrees C to Kelvin. So that's degrees C to K. To go from degrees C to Kelvin, you're going to add 273.15. So for example, 25 degrees C is 298.15 Kelvin. And then we go from Kelvin to degrees C. And for this, we're going to subtract 273.15. So 50 Kelvin is equal to minus 223.15 degrees C. A couple more points about the Kelvin scale is number one, it does not have any negative values. So the lowest value is 0 K, and you cannot have a negative value. You cannot have a value lower than 0. And the second thing is that 1 unit change on the Kelvin scale is the same as the Celsius scale. So for example, if you have a temperature change of 10 Kelvin, it's the same as having a temperature change of 10 degrees C. So in the DP chemistry course, you're going to be using both temperature scales, that's the Kelvin scale and the Celsius scale, and you should know how to convert between the two. So next we have the relationship between average kinetic energy, which is on the y-axis of this graph, and temperature in Kelvin, which is on the x-axis. So as we can see from the graph, the temperature in Kelvin is directly proportional to the average kinetic energy of a substance. So let's say you have two substances, one at 200 Kelvin and one at 400 Kelvin. Then the substance at 400 Kelvin has double the average kinetic energy of the substance at 200 Kelvin. So it's a directly proportional relationship between temperature in Kelvin and the average kinetic energy of the particles. So finally, we look at changes in energy as a substance is heated and undergoes a change of state. So this diagram shows the heating curve for water. So we start on the bottom left where we have water as a solid, which we know as ice. As heat is added, the temperature of the solid ice increases until it reaches 0 degrees. At this point, the ice starts to melt. What you'll notice here is that as the ice is melting, the temperature does not change. This is because the heat that's added is being used to overcome the intermolecular forces between the particles in the solid. Once the ice is melted, we then have liquid water, and we then start to see the temperature increasing again, until we reach 100 degrees C where the water starts to boil. Once again at this point we see that even though heat is being added, there's no change in the temperature. And this is because the heat added is being used to overcome the intermolecular forces between the particles. And once those intermolecular forces are overcome, the liquid is now a gas, which we call steam. So for any substance, you'll see a similar shaped heating or cooling curve. When a substance is being heated, there's an increase in the kinetic energy as the temperature increases. When a substance starts to change its state, for example melting or boiling, there's no change in temperature even though the heat is still being added. And this is because of the heat added is being used to overcome the intermolecular forces between the particles instead of increasing its temperature.